In this video, we do pretty much the same thing that we did in the last couple of videos. We've got a function and we want to determine whether the function is increasing or decreasing. We want to determine whether the graph of the function is concave upward or concave downward. And then once we have all that information, we'll graph the function and we'll use a first derivative test to find any relative extrema, and we'll confirm our results from the first derivative test using the second derivative test. So first, to determine the intervals where the function is increasing and then the intervals where the function is decreasing, we need to compute the derivative. So we've got the derivative of a quotient, which requires the quotient rule. Now remember, the derivative of a quotient has a mnemonic associated with it. The derivative of high over low. Of course, it's not how we spell high and low, but it just helps us simplify what we write, is low d high minus high d low over low low. And that d is an operator. It applies to whatever's in front of it. So you're actually taking the derivative of the top function or the derivative of the bottom function. So when I'm evaluating this derivative, this is my low function. So low d high is the bottom function times the derivative of the top function. The derivative of 10x squared is just 20x. And then we subtract high, which is at 10x squared. And we multiply by d low. The derivative of x squared is 2x. And the derivative of 1 is 0. So we just get a 2x. And then we're dividing all of that by the quantity x squared plus 1, quantity squared. Now, if we simplify that, we've got 20x times x squared is 20x cubed. Plus 20x, because 1 times 20x is 20x, minus 10 times 2 is 20, x squared times x is x cubed, so minus 20x cubed. So those reduce, and then we're dividing by x squared plus 1, quantity squared. So f prime is just this 20x divided by x squared plus 1, quantity squared. Now to determine the intervals where the function is increasing and decreasing, first we need to find the critical values. The critical values are those x values that correspond to a zero derivative or a derivative that's undefined, and they also have to be in the domain of the original function. Now, the domain of the original function is all real numbers. This denominator is always greater than or equal to 1. So we're never dividing by 0 here. So the only critical values in this case correspond to x values that cause this derivative to be 0. We might say, well, this would be, f prime would be undefined when the denominator is 0, but the denominator is never 0. So we'll say, okay, I'm trying to find the critical number. So I say f prime is equal to 0 when the numerator is 0 and the denominator is non-zero. And this is already non-zero all the time. So that'll be 0 when the numerator is 0. And that means that x is equal to 0. So f prime is 0 when x is equal to 0. This is our one critical number. And f prime is well defined for all real numbers. So we have a single critical number there. So now I can draw my sign chart. And it only has the one critical number on it. Now f prime is 20x in the numerator divided by x squared plus 1, quantity squared. X squared plus 1, quantity squared is always positive, and 20x is positive when x is positive and negative when x is negative. So f prime is a negative times a positive on the interval from negative infinity to 0, so that makes it negative. And then it's a positive times a positive on the interval from 0 to infinity, so that makes it positive. So our function goes from decreasing to having a 0 slope to increasing. So that means that f of 0 corresponds to a relative minimum. So I'm going to write that down. F of 0 is just 10 times 0 squared divided by 0 squared plus 1, which is of course 0. F of 0 is a relative minimum. So we found the critical numbers by computing f prime, setting f prime equal to 0 and solving for x. And then we also thought about finding any x values for which f prime was undefined. There weren't any. Then we made our sign chart. So we said we only have one critical number. We'll draw that on the number line. We'll list the factors of f prime over here, and then find the sign of each factor on each of these intervals, and then multiply those signs together to get the sign of f prime on each of the intervals. Then once we have the sign of f prime, we're able to say that since the function goes from decreasing to increasing at that x value, we must have a relative minimum. And that's the first derivative test. So we're asked to identify the intervals where the function is increasing and the intervals where the function is decreasing, and we've done that. When f prime is positive, the function is increasing. So f is increasing on 0 to infinity and decreasing on negative infinity to 0. Okay, so we did that. We took care of those two tasks. Now we want to do pretty much the same thing with the second derivative to determine where our graph is concave upward and concave downward. And so we will compute the second derivative now and look at where it changes signs. F double prime of x is the derivative with respect to x of the first derivative, and the first derivative was 20x divided by x squared plus 1 quantity squared. So we're going to use that mnemonic for the quotient rule again. It's low, bottom function, d high. So we're multiplying by the derivative of the top function. It's 20 minus high, d low. Now, the derivative of the bottom function actually requires the chain rule. We've got an inside function and an outside function. So when we take the derivative of this function squared, well, we get 2 times the original function raised to the 1 less power, which is 1. And then we always put the inside function back inside. And then we multiply by the derivative of the inside by the chain rule. And in this case, the derivative of the inside is 2x, but I wanted to write it out just to make sure that I covered everything. And then once we write that out, we're done. So we've got low d high minus high d low, all divided by low low. Got x squared plus 1, quantity squared squared. If I square something twice, it's going to give us, raise it to the 4th power. And we said that this is 2x. So now we can simplify. I've got x squared plus 1 quantity squared times 20. And then I've got 20x times 2 is 40x times another 2x is going to be 80x squared. And then I'm subtracting that. So I have minus 80x squared times this x squared plus 1. And all of that is divided by x squared plus 1 raised to the 4th. Now notice that in the numerator, we've got an x squared plus 1 squared here and an x squared plus 1 to the 1st here. So we have a common factor. When I look at this this term and this term, they both have an x squared plus 1 in common. So I can factor that x squared plus 1 out. And then I just ask myself, well, x squared plus 1 times what will give us this? Well, we need the 20, and we need another x squared plus 1. And then I say x squared plus 1 times what will give me this? And it's going to be that negative 80x squared. So that's what I have there. And this reduces with one of those, so I'll have 3 of them. If I distribute that 20, I've got 20x squared plus 20 minus 80x squared. And we're dividing all of that by x squared plus 1 quantity cubed. And 20 minus 80 is negative 60. You end up with 20 minus 60 x squared, all divided by x squared plus 1 quantity cubed. And if we want to, we can factor out that 20. That 20 times 1 minus 3x squared, all divided by x squared plus 1 quantity cubed. Okay. Provided I didn't make any mistakes, my calculation or any calculation errors, that should be my second derivative. Okay, so the question is, well, when does the second derivative change signs? What are the critical values, or not critical values, but something similar to the critical values for our second derivative? Well, to find that, we just set f double prime equal to 0. That fraction will equal 0 when the numerator is 0 and the denominator is non-zero. The numerator and denominator don't have any factors in common, so we can just set the numerator equal to 0. And then when we divide both sides by 20 and add 3x squared to both sides, we get this. And so we'll have x squared equals 1/3. And then if we take the square root of both sides, we get x equals plus or minus the square root of 1/3. Now those are potential x coordinates of points of inflection. Now, to determine whether or not those actually correspond to x coordinates of points of inflection, we have to look at the sign, the SIGN sign of that second derivative. Now, f double prime gets a number line as well. We're going to make a sign chart for f double prime, and then we'll list our x values that cause f double prime to be 0. And then we would also list any x values that cause f double prime to be undefined. But this is well defined all the time. X squared plus 1 is always greater than 1. When we cube it, it's still greater than 1. So let's say f double prime is always well defined. So we're fine there. So these are the only numbers that go on our number line for f double prime. And f double prime is 20 times this times or divided by that. And then I just look at the sign of each of these factors on each of these 3 intervals. And then I use the signs of these factors. I multiply the signs of these factors together to get the sign of f double prime. So 20 is always positive no matter what x is. X squared plus 1 is always positive. So when we cube it, it's always positive. And then 1 minus 3x squared actually looks roughly like this. When x equals 0, we're going to get a 0. And then when we subtract 3x squared, it's going to be a parabola facing down. If that 3 weren't there, it would just be 1 minus x squared. It would be just exactly what we would expect. But multiplying by 3 just means the original parabola was 3 times as tall. So we made it 3 times as tall, then we flipped it upside down, and then we moved it up 1 unit to get this graph. So our function values for this function are determined by the y values on the graph of y equals 1 minus 3x squared. Well, when my x value is less than negative square root of 1/3, I'm going to be over here. So the y values are negative. So I'm going to get a negative answer there. Now, between the negative square root of 1/3 and the positive square root of 1/3, our y values are all positive. So we get a positive answer. And then to the right of x equals the square root of 1/3, we're going to get a negative value. So I can just read this graph to determine those signs. Or alternatively, you could pick an x value. You could substitute in x equals -1 here, and you'd get 1 minus 3, which is -2. So that's negative. You could substitute in x equals +1 here, and you'd get 1 minus 3, which is -2, which is negative. And if you substitute in x equals 0, you get 1 minus 0, which is 0, which is positive. And so that's another way. Just choosing test values can get you the correct signs as well. But I just like to read the graph, especially for these parabolas that are upside down. We see them a lot. Now, f double prime is a positive times a negative divided by a positive. So that's going to make it negative. And then it's a positive times a positive divided by a positive, which is positive. And then it's a positive times a negative divided by a positive, which is negative. So that means, well, anytime our f double prime is negative, our graph is concave down. It's going to look roughly like that. And then in between, it's concave up. And since these x values correspond to places where the graph changes from concave downward to concave upward, or concave upward to concave downward, these are the x coordinates of our points of inflection. So our points of inflection are x equals the negative square root of 1/3, and the corresponding y value. And x equals the positive square root of 1/3 and the corresponding y value. Now our function was, let's see, 10x squared divided by x squared plus 1. So we're substituting plus or minus the square root of 1/3. And then we're squaring that. So this is going to be 1/3 times 10, which is 10/3, divided by 1/3 plus 1. 1/3 plus 3/3 is 4/3. And that reduces to 10/4. And we can divide that by 2, whoops, and get 5, and divide that by 2 and get 2. So we get 2.5, or, well, 2.5. Now, I actually don't know a numerical approximation of the square root of 1/3. Okay, so those are our points of inflection, and our graph is concave upward. On negative, the square root of negative, or -1 times the square root of 1/3 to positive square root of 1/3. And it's concave downward on the other intervals. Okay, so we know where our graph is points of inflection. We know where it's concave upward and concave downward. We also know that it has a relative minimum of 0 at x equals 0, and it's decreasing on this interval and increasing on this interval. So with all of that information, we can graph our function, but I actually need to know what approximately the square root of 1/3 is. So I'm going to use my calculator to figure that out. Okay, so we know where our graph is concave upward, concave downward. We know where it's increasing and decreasing from our work on the previous page. I did use the calculator to approximate those values, and they're approximately negative, plus or minus 0.58. It's actually 0.577. So those are our points of inflection. So if we wanted to, we could make a number line for the graph of the function. And we could include all of these values. We could use the negative square root of 1/3, the 0, and the positive square root of 1/3. And we could say on these 3 or these 4 intervals, what are the signs of y prime and y double prime? Well, the function is increasing on 0 to infinity, so y prime is going to be positive there and there. It's decreasing on negative infinity to 0, so y double prime is negative there and there. Or excuse me, y prime is negative there and there. And then y double prime is positive between the negative square root of 1/3 and the positive square root of 1/3. So it's positive here. And then it's negative on these 2 intervals. Now with those pieces of information, and then these 2 graphs, here is a graph that's concave upward. And then it's decreasing on the left and increasing on the right. And then we've got concave downward here. And it's increasing on the right, or excuse me, on the left, and decreasing on the right. With those 2 graphs and this chart, we can, and these points, the 2 points of inflection and the f of 0 equals 0 corresponded to a relative max, I think. No, it was a relative min by the first derivative test. Remember, because we did that calculation right there. The function went from decreasing to having a 0 slope to increasing. We can use all of that information to graph our function. So let's graph it. And remember, our y was equal to 10x squared divided by x squared plus 1. So here's a fact. If we take the limit of this function as x goes to positive or negative infinity, we have a 0 over 0 indeterminate form, or excuse me, an infinity over infinity indeterminate form. But if we divide the numerator and denominator by x squared, we can get rid of that indeterminate form. And we end up with 10 divided by 1 plus 1 over x squared. And now it's not an indeterminate form anymore. The numerator is just approaching 10, and the denominator is approaching 1 plus something going to 0, which is 1. So this limit is 10, which tells us that y equals 10 is a horizontal asymptote of the function. And we could see that. We know the degree, if the degree of the numerator and denominator, if both of those degrees are the same, y equals the ratio of the leading coefficients is the equation of the horizontal tangent, or excuse me, the horizontal asymptote of the function. But this is how we prove it. We get rid of the infinity over infinity indeterminate form by dividing by the highest power of x, and then we get this asymptote. So this function approaches y equals 10 as x goes to positive or negative infinity. Now we know that at x equals 0, our function is 0, and that's supposed to be a relative minimum. And what else do we know? At x equals negative 0.58, the y value is 2.5, and at x equals positive 0.58, the y value is 2.5. And that makes sense because of the symmetry. If we've got this x squared everywhere, here's negative 1 and 1. And I'm just going to try to divide this into 4 equal pieces. So at negative 0.58, the y value is 2.5. We have the same thing on the other side. It's supposed to be points of inflection. And the y value there is 2.5. Okay. And now we've got our sign chart here. On the interval from negative infinity to the negative square root of 1/3, the function is decreasing and it's concave down. So, and we know it's also approaching this y equals 10 as x goes to infinity. So if it's decreasing and concave down, it's going to look roughly like this. So that's what we have there. Now here on this interval, the function is decreasing and concave upward from the square root of, or negative square root of 1/3 to 0. So if it's decreasing and concave upward looks like this, and then decreasing, the decreasing part of the concave upward graph looks like that. So I'm gonna go like that. Now from 0 to the positive square root of 1/3, it's increasing in concave upward. We'll just draw it like that. And then from the positive square root of 1/3 to infinity, the function is increasing in concave downward. So here's concave downward, and the increasing part looks like that, and we know it's approaching this line. So it's going to look like that. So these two are points of inflection. And then we have a relative minimum of 0 at x equals 0. The minimum value is the y value. The x value is where that minimum occurs. And we don't have a relative maximum. We don't even have an absolute maximum because the function gets arbitrarily close to 10 as x goes to positive or negative infinity. Let's confirm this on desmos.com. Make sure that our graph is consistent with what we see when we use a graphing calculator. So this is our graph. And these points are not the points that we're looking for. Oops. Oops. And the other point is just like it, but the X values are negative. And I think that's consistent with our intuition. I want to zoom in a little bit. Let's let our X's go from -4 to 4. Makes it a little bit more obvious that it's concave upward here and concave downward here, if we zoom in a bit. And the claim is that these points of inflection correspond to points where the second derivative is 0. And they do. The second derivative is 0 right there. So at -0.577 and positive 0.577. And the second derivative is positive on the interval from here to here. And that's where the original graph is concave upward. And it's negative on the interval from -infinity to that X value and this X value to infinity. And the graph is concave down there and there. So that's good. And then if we look at the first derivative, the first derivative is 0 right here. And the function is increasing on the interval from 0 to infinity, and the Y values on the derivative graph are positive, so that's good. And the function is decreasing on the interval from -infinity to 0, and the Y values on the first derivative graph are negative, so that's good. Now, if you want to compare Y prime and Y double prime, you can. Now, Y prime or Y double prime is the derivative of Y prime. So if this is Y prime, we can see that it has a 0 slope at this X value and at that X value. So we would expect the derivative to be 0 or the derivative of the first derivative, the second derivative to be 0 at this X value and this X value. And the derivative is 0 there. F prime is increasing from that point to that point, and the second derivative is positive on that interval. And F prime is decreasing from -infinity to that X value, and the Y values on the graph of F double prime are negative there. And then F prime is decreasing from this X value to infinity, and the Y values on the graph of F double prime are negative there. So we can see sort of the relationship between when those functions are increasing and decreasing and what the graphs of the derivatives look like. There are some quiz questions in my class where I'll give you one of these functions. So I'll say this is F prime, graph F double prime, and graph F, for example. And you should be able to determine, well, that F has a relative minimum here. I can look at the slope of this graph to find out when the second derivative should be 0. But basically, if you have one of those graphs, you have enough information to infer the information for the others. It would just be an estimate. It won't be perfect, but it'll be close enough that you can have a very good idea of what the second derivative or the first and second derivative should look like if you're given the original function, or what the second derivative and the original function should look like if you're given the derivative, and so on. So that's the idea. Our graph on paper, or excuse me, on Desmos looks like the graph on paper. And those do correspond to points of inflection. You see it's concave up there and concave down there and concave down there. So it looks like we did our job correctly. It looks like we know what we're doing.